Okay, welcome everyone again, and congratulations in reaching this far of the course. This is the last sessions we will have on Bayesian data analysis, so congratulations again and thank you for being here. This session will be about more complex methods because we will review how to do some psychometric analysis with Bayesian perspective. More concretely, first of all, I will get into reliability estimates, and then the main dish of this session will be Bayesian structural equation modeling, and I will finish with some emergent methods or more advanced techniques that are in development or that they are just pretty established but very complex. For example, Bayesian RRT models. Okay, so let's have a quick recap on Bayesian inference, and then I will also make a quick recap on psychometrics, and to then see how they can combine each other. Okay, so in Bayesian inference, remember that we have posterior distributions that are the result of combining data likelihood with prior distributions, so that need to be specified. And many times we need to create approximations or estimate these posterior distributions with analytical methods or with simulation-based methods. For example, Markov chain Monte Carlo methods that have some technical properties that need to be addressed. Thanks to that, we can create prior and posterior plots, credibility intervals, but also bias factors, robustness analysis, sequential analysis, etc. And this is the typical example of a simple test doing in a Bayesian way with prior, posterior, descriptive information, robustness check, bias factor, sequential analysis, etc. Okay, so now regarding the psychometrics, I want to address what, in my view, is a very good way of summing up the discipline. Psychometrics is basically the scientific discipline of measuring psychological phenomena. Okay, so I would say that psychometrics is based mostly in the psychometric inference, where we create tests that are basically sample of behaviors, and with scaling techniques, we can create observed scores from these tests or this sample of behaviors, for example, a Likert scale, or counting the errors or something like that. Then these participants' responses that can be considered as observed scores through the reliability process and having some guarantees on reliability, if we consider these scores to be reliable, we can consider them as proxies of true scores, of the real scores of the participants in this trait or skill that we want to, or process that we want to measure. Then through the validity analysis or the validity guarantees, we can infer that these true scores reflect the construct that we want. And if we manage to get there, our gained knowledge of this construct can be used for the improvement of new tests and other things in psychology. Okay, so reliability and validity are the two main processes of psychometrics, and regarding reliability, there are many sources: internal consistency, temporal stability, inter-rater agreement, etc. I will focus on internal consistency regarding Bayesian analysis. And regarding validity, there are also many sources like content-based validities with stable specifications, etc., latent structure with explorative factor analysis, confirmatory factor analysis, invariance analysis, etc., but also relations with other variables like positive and negative association, multi-trait, multi-method matrix, path analysis, psychometric networks, etc., and also other sources like response processes, social consequences, etc. I will focus on here on latent structures regarding Bayesian structural equation model. Okay, so now my first stop will be on internal consistency, because we can create Bayesian versions of internal consistency analysis. Okay, so this is the very short and simple example of a frequentist internal consistency analysis. We have this test that is the WHO5, a really short test of only 5 items to measure well-being. And the items are: I have felt cheerful and in good spirits, I have felt calm and relaxed, I have felt active and vigorous, I woke up feeling fresh and rested, and my daily life has been filled with things that interest me. They have a 6-point Likert scale from 0 to 5. 0 is never, 5 is always, you can see there. And we have in a dataset a frequency scale reliability statistic, for example, Cronbach's alpha, McDonald's omega, but also other alternatives like Goodman's lambda 6, greatest lower bound, average inter-item correlations, and other information. Okay, so you can see here that regardless of what we choose, the reliability estimate seems to be around 0.8 with something, 0.8. Okay, so many of you can consider this appropriate. I consider it appropriate, but maybe there's some debate that it should be higher into 0.9 or it can be lowered into 0.7 to be acceptable. I would just consider it as standard, okay? If we want to improve reliability, we can screen the 5 items into do an if item dropped, how do you say, if item dropped analysis, and see if any of our indices of internal consistency get increased when we remove one single item. And as you can see here, there is none of the case, so it seems that the scale seems to be pretty good. And finally, JASP can provide you of a preliminary confirmatory factor analysis output to be sure in a quick way that you have an unidimensional structure, because remember that these indices rely on the assumption that you have a unidimensional construct. Okay, so this is a frequency example. How we can do that from a Bayesian way? We can do that, and actually we will need to specify the priors here to get the likelihood and create a posterior. And the priors will be these ones. Regarding alpha, lambda 6, and greatest lower bound, we will count with an inverse Wishart distribution that has a scale parameter, can be the informativity of this distribution, and also degrees of freedom, that is basically the number of items. For the omega, it's going to be special because we have an inverse gamma distribution combined with a normal distribution. So we have a shape and scale parameter, but also a mean for this normal distribution. And the general rule is that if we have a new scale, non-informative priors should be preferred, and if we have existing scales, informative priors should be preferred. Then MCMC will start. Remember, the number of chains need to be appropriate, having enough iterations, enough burn-in iterations to be efficient, thinning if it's necessary, etc. And if everything goes okay, we will have a posterior with its maximum and credible interval for the overall index, and also the if item drop statistics. We also have the density curves, and also if they are between acceptable values, for example 0.7 and 0.9. And also we will have this CFA preliminary evidence that everything is okay, but with Bayesian fit indices. I will elaborate that in posterior videos, and also some MCMC diagnostics. So this is a typical example of a Bayesian reliability analysis. As you can see here, we have omega, alpha, lambda 6, and GLB. Most of them in a similar way, around 0.8 with non-informative priors, as you can see here. And here are the density curves of the posteriors of the if item drop statistics. And as you can see here, the overall scale is above all of them. So therefore, there is this is a very quick way to see that there is no need for removal of any item, because all of them contribute, and actually the one that contributes the most is the first item. And as you can see here, we can be pretty sure and pretty confident, as the posterior is, that we got 0.8 around in internal consistency. This information can be displayed in a table format, as you can see here. This is the overall indices, and these are the if item dropped analysis. But also we have this table that is the probability that this reliability statistic is larger than 0.7 and smaller than 0.9. With the priors, as you can see here, they are very small because we got non-informative priors. But in the posterior, we have that they are basically 1. They are super high, so that's pretty good news. Okay. Now we have more information. These are MCMC diagnostics, the trace plots. As you can see here, everything is okay. We could make more, we could ask for more, for example, PRSF or R hat, effective sample size, or something like that, but here is not necessary. And we also have this preliminary confirmatory factor analysis from a Bayesian point of view to see if everything is correct. So we can see that CFI until I are okay, but the root mean square error approximation is not. And we also have the standardized loading that it seems to be everything okay. And finally, we have the posterior predictive check to see if it is essentially an unidimensional solution, and we can see here with the credible interval that it seems to be an unidimensional solution. So everything seems to be okay with non-informative priors. This is the same example, but with informative priors. As you can see here, the little curves are over here. And now, as you can see here, the data is so strong that there is no much difference. The information is essentially different, but the difference is little because we are not able to be that strong like data. And this is the same information as before. Now, as you can see here, the prior probabilities are higher of being in the good zone. And also you can make more informative priors to be super certain about this. And finally, we have the technical information that is basically the same. Everything is going more or less the same way, and we have more or less the same things. Okay, now I have introduced a problematic item, an item that is from a different scale. As you can see here, it's an item from the NEO 5-factor inventory. And now we can see that even with informative priors, now we have a decrease in internal consistency around 0.8. Not 0.82 or 0.83, we are now at 0.8. And if the curves of the if item dropped statistics are very clear about this. There is an item that if you remove it, you will have a higher internal consistency, and that's pretty good, actually. That's a pretty visual way to screen for problematic items. But remember, these are one of the factors of the NEO, all of the items respected to these factors with all of the indices. Remember that removing items to increase internal consistency can be problematic because you are sacrificing replicability and generalizability and also content-based validity to increase precision. So you need to make an informed decision within a context. Okay, so that's it for internal consistency. So as you can see here, you can make a Bayesian inference on that. The only problem is that you need to have some knowledge about the priors and how they interact with the parameters. And if you want to make an informative prior, you need to be really certain of what you are doing. Okay, so in the next video, we will address structural equation models.